Today I'm going to talk about linear regression, just the intro to it, so we understand like some things for machine learning. This is usually used for machine learning. It's an algorithm for machine learning. It's not too bad. It's not too much math. It just requires some basic high school math that you should just understand, like algebra. So I can show you what it is. So what is, first we got to talk about what it does. It's for quantitative data. We want to predict something numerical. That's why we use it to predict something numerical. And we can it can be like anything numerical, like you're given a height and it wants to predict the weight based on that height. So for example, if you're given I can show example, predict weight given height. Notice that these two are numerical quantities. Because they're numerical, we need linear regression. And I'm going to show you why. The reason why it might be so the reason why now is because of the word linear is very important. It's the key thing in linear regression, is the linear word. And if you think of linear, then you think of a line, right? Like something like this. This is a linear line. And this is used for predicting. So you can see example, like if we have something like this, and we're graphing something like this, we have this here. This is the y-axis, and this is the x-axis. This is going to be used for prediction. So we can say the x is the height. We're given the height of something, and we want to predict the weight. It's a linear relationship. So it can use these data values for training, and then you can predict another ones based on it. So you can think of this, well, this line is really the model. This line is the model. Okay, so don't get confused with what is this model. I don't understand this training things. It sounds very complex, but it's really just this. It's very simple. The model, this is the most simple model you can make, a linear model. So it's a linear. That's why it's called linear regression, because of it's a linear model. Yeah, so this model is going to predict based on this line. Okay, and this line's equation is very important for for programming it. I'll show you that. But we can go and see it. It's going to be y. The prediction, though, this is the prediction line. The actual data points will be something like this. It will be around it like this, some weird pattern. It's going to be something like this. These are going to be the data points. They're not going to be exactly the best. Why did I draw some line there again? But it's not going to be the best data points. That's why we use this line of best fit. It's called the best fit line. So really all the data points are going to be there. It's going to try to capture that behavior. So this line, our model, really, it's not really a model, but think of it like our model basically. The line, the best fit line, is capturing the behavior of the data linearly. Okay? Linearly, it's capturing the data basically. So let's see, it's called, and we're gonna call it for the formula, they call it y hat, capital Y hat, and that's equal to, it's basically a linear equation. So the slope, they use the Greek letter beta, and they have some weird stuff after that, but I'm just gonna write m sub m for the slope, basically because y equals mx plus b, where m is the slope, so we're gonna have a subscript so it is less confusing, but I'll keep the beta so you don't get confused with the other ones on the internet. And then remember, this is the slope, so we have the x, which is basically the height, given the height, and then we add in the y-intercept. This one is just example starting from 0, but it could be any y-intercept. We can, I'm gonna go and name it beta again, sub b or sub y, it doesn't matter. But really there's a y here, y hat. There is a hat to make it different because it is the prediction basically. And then we have epsilon for the error. Okay, so we have to add in the error. This is the error. And then, basically this error, because if it looks mysterious, this epsilon, which is error, is equal to the actual value minus the prediction. Sub I, I'm having a sub I for any prediction or any predicted value. That is what epsilon is. So we can even substitute it in there. But this is going to be very important for the mean squared error, which is how we can evaluate this model. So basically, now as this model done, we want to see like the error, because we want to minimize error. We don't want that much error. So that's why we got to try to evaluate the performance with mean squared error, which is the metric, the evaluation metric, mean squared error, MSE. That's the evaluation metric they use for evaluating this model as a whole. How much error does it have? I mean, really, that's because of this one. It gives you for each data point how much error there is. Epsilon doesn't give us that much stuff, just only for each data point. That's why we're going to use mean squared error. And if we recall what the mean is of anything, what is the mean? This is exactly what it sounds like, basically. But let me show you. What is the mean? It is equal to the sum of the data points. Some of the data points, it's called the data points. I don't want to say X, but let's say data. Some of the data divided by the number of them. This is what we're going to use, except we're going to take the mean of the error squared. So we're going to see that the mean squared error, MSE, is very important. But we're going to see what this is. So we need the mean, so we're going to have 1 over n, and also to like normalize it, 1 over n. And then I'm not going to have enough space. So let me go move this. You probably know, you should know what epsilon is, right? Let me just write it in here, very small. For any error, I forgot to add a sub I there. You go to y I minus y hat I. Just remember, this is a y prediction. This line's basically this line prediction versus the individual data point that it's closest to. We're basically finding the distance, really like the distance between those points. Okay, so now we're going to see the mean squared error. Taking the sum now, we have that for normalizing, and we're taking the sum. And we're going to go start at I equals 1 and go to n, which is the number of data points. That's what we're dividing by it also, and we have the error. Basically square that error, and this is the mean squared error. Or you can write it like this. I think they have a sub I there also, but that's it doesn't matter. You don't really need to write it. You just have to understand what is the meaning. Y I minus y hat I squared. This is the mean squared error. This is how you would see it traditionally written like this, but you can also write it like that. They're the same. And the purpose of epsilon is the error, basically, and then we have the mean squared error, which is going to give us the evaluation, which is the evaluation metric for this entire model that we have. When we go over like more things like classification, that gets more complex. Like this is like the mechanics behind it, the math. So then this could probably help you with creating the model actually and programming it. So I hope this lecture makes sense, and we'll be talking next time.